Okay, I think we're ready to start. Okay. It's a great pleasure to have Dr. Mose coming here to give a colloquium today. He graduated 2008 from UPenn. Okay. He had a BS from Princeton University, and he had a graduate student from University of Pennsylvania at UPenn. And after that, he spent 3 years at the University of Cambridge, okay, real Cambridge, England, Cambridge. Okay. Then I guess it's enough off the other side, and he came back to New York City, Rockefeller University, and he spent close to 5 years at the Rockefeller University, working on nice structures. Okay, so that's something you can talk about. Actually, it's not something like this, but this looks nice. Okay. And
related to that, but not.
Yeah, that's an appreciation for you coming here to do the talk, token of appreciation. The physics department presented you a small gift.
Oh wow! Thank you so much. Thanks for having me. It's a very, very kind invitation.
So the floor is yours.
Thanks. Thanks for everything. Show off. Beautiful mug. Thank you so much. I'm sure I'll drink lots of coffee out of this. So so I'm going to tell you a bit about some work I've been doing the last couple of years at Rockefeller with Marcelo Magnasco and our collaborator at Penn, Elena Catafori, on complex spatial networks and what we can learn, what is difficult, and how these things are related to problems that we actually might care about. And please, if at any time you have any questions, please interrupt, and we can be happy to have it back and forth. So hopefully this is instantly recognizable to everyone, right? This is the classic map of the London Underground. Part of the reason why this is so iconic is because it so efficiently encapsulates information about a complex network. Now this is not a spatially embedded network. This network is 2D or quasi-2D, depending on how you want to look at it. But regardless, we have, as humans, there's something special about a two-dimensional network that you can look at and just immediately understand how all the pieces fit together. Even if you've never been to London before, and you were standing in Green Park and you wanted to make it up to King's Cross and Pancras and try to find the 9 3/4, right? The platform 9 3/4 to make it to Hogwarts. You can figure out how to get there very easily, right? You know how all the connections work. You know what you need to do, and so that's fine from an informational sort of condensation point of view. But it also turns out that there are physically relevant two-dimensional networks out there as well. So leafidation is a really interesting, beautiful example where if you look very, very closely at most leaves, deciduous leaves, the kind of dominant clades of plants that exist in the world today have this sort of rich, loopy, complicated two-dimensional network structure where even if you look by eye, it looks sort of vaguely hierarchical, where you have some kind of main vein structure and then something that's sort of next largest that sort of makes it, if you look at these next largest sets, they sort of make a little tiling, and then they are all individually tiled by next largest sets and so on and so forth. And so there's some sort of rich sort of fractal looking geometry to that. And you might ask yourself, but why would nature elect to do this? Why is this a dominant strategy among clades of plants these days? Why did this come out? Especially when a leaf is sort of the classic example of something that wants to transport material from one spot, the entry of the main vein, to many other spots, the rest of the leaf. And you can actually prove, mathematically, it was done a long time ago, that the most efficient kind of network to do this sort of single point to multiple point transportation is a tree-like graph, right? You're wasting construction effort and you're wasting the pressure drop by having all these extra interconnections. And so one answer to the reason why, and there are many, but one, the easiest to see, is that it gives you a backup system. It gives you resilience to damage. So this is a lemon leaf where there's a fluorescent dyes being pumped through, and a hole has been cut through the main vein, and of course, because of this reticulation, you're able to get backfill, and ultimately everything functions totally as it should. You don't get any degradation or tissue that doesn't get irrigated. And just because these pictures are pretty, I'll show another. But different leaf geometry, less symmetric. Well, it has this sort of reflection symmetry, but it's not a nice smooth curve, right? It has these extra bits, but it doesn't matter. It still all totally fills in. So I said that this clade was dominant. There are still some of the old ones left. Ginkgo biloba belongs to an evolutionarily old clade of plants, and it does not have this adaptation. And of course, this is a major problem for it. So complex networks, when you're in a complex setting like the battle of evolution and life, having complex networks turns out to be a good thing. And there are, as I alluded to before, there are other reasons, and we can talk about that later. But I want to move on to another example of a nice complex network system. So if you've never seen or heard of this slime mold, this is the Physarum polycephalum slime mold. It's sort of generated a lot of interest in the last 5 to 10 years in the sort of networks research community, largely because of how dynamically adaptive it is on a relatively short time scale. So what this slime mold does, it lives in forests, and it likes to eat. So this is a dead log, a tree that's fallen down that's eating. This is macroscopic. This is not, I should put some kind of scale bar in this, but this is not to size. It's smaller than this, but it's not macroscopic. This is probably a few inches to a foot across, something like that. And this is a single cell. This is a single-celled creature. It's a slime mold with many, many nuclei. And it makes this very, very complicated network structure. It has areas where it's eating, and then areas where it's looking for new good spots around the wood, where it sends out these fans. Sort of see at the top here. This is exploratory. How it behaves. And the thing that sort of captured people's interest about this network as a dynamical system, there was a paper that appeared 5 years ago or so in Science that showed that if you take one of these things and you prepare a petri dish and you cut out some region around in the agar, so everywhere where the pointer is currently kind of moving, so you remove the agar and you just fill in with something that's completely not amenable to the slime mold, and then you put down these little dots of light are oat flakes. And this pattern is meaningful. This pattern of oat flakes and the area that you cut is a representation of the local environs of the city of Tokyo. All the oat flakes are population centers around Tokyo, and the very large oat flake that the slime mold is introduced to the sample on right there is the location of Tokyo. And you let it go over the course of one day. First it does this exploratory phase. It just sends the tendrils out everywhere, and there's kind of a dense net of network tubes. I'm sorry, it goes down this way. So it sends the fans out, and once it sort of covers all the available ground, it starts pairing off the exploratory tubes. It no longer needs to find food, it found food. And now it just needs to keep itself connected in the best, most efficient way possible to redistribute the food and the resources around the entire organism. And so by the time the end of the day passes, all the exploratory fans are paired back, and you're left with this complicated two-dimensional network that, by the way, really is a dead ringer for the Tokyo rail network. So this is a single-celled organism that is somehow smart, right? And that's captured people's imaginations with this thing. And so this, again, this is still just 2 dimensions. And so you can actually attack a 2-dimensional problem. Part of the reason why the first image, the image of London Underground, is something that is so, it immediately talks to you and you understand it, is because the problem in 2D turns out actually not to be that hard as far as characterizing things. You can map a network in 2D onto a tree graph. You can think of it as a sort of immersed set of tiles that you cut away. And the way that that works is that you have some little section of the tree graph, and you assign weights to the tree graph. So it depends on the problem that you're looking at. In the case of the London Underground, it could be passengers per hour. In the case of the leaf venation, it could be just the diameter of the tubes in the leaf, or it could be the pressure drop across a particular branch, depending on what specific property you care about. But you assign weights to the edges. And then you remove the edge with the lowest weight. So there's some specific edge in the system that you care the least about, that's contributing somehow the least to workings of the network because it has the least flow in it, or whatever ordering it shows. And so when you do that for a 2D network, the tiles, or the polygons that edge were coincidence with, now become one large tile. And you can imagine that as a branching on a tree graph. This is what I meant by sort of a reverse inversion of a coalescent tree graph. And then you can iterate. So all these, the final nodes on the tree graph are the tiles in the network that you started with, and then you cut an edge and two of the tiles come together here, and then you cut the next weakest edge, and two more of the tiles come together like this, and you just iterate until you can't do any more cuts. And you create a representation of a loopy 2D graph as a tree graph. And tree graphs have been studied for much longer. They're more kind of robust objects to play with mathematically and characterize mathematically. And so you can say some things directly about the hierarchy, the fractal structure of the graphs this way. I'm going to forgive me, I'm going to cycle back around to that. But I want to first talk about networks in 3D. So this is the meat of what I actually want to say. The 2D examples are nice, right? Transport networks are important. Leafination is interesting, and you can learn things about transport networks from things like leafination, and the slime mold's cool. But really, most of the crucial spatially embedded networks in the world are three-dimensional networks. So the pattern of interconnections of the neurons in the brain is a complicated 3D network. This is another one that's maybe not important per se, but is sort of interesting, and not a lot of people know it. The root structure of quaking aspen makes a complicated three-dimensional network. The reason why sometimes you see pictures, usually in the Rockies, I'm not sure if there are any quaking aspen around here, I don't think so. But the reason why sometimes in those pictures you'll see a large chunk of trees that have all turned the exact same color of their leaves in the fall is because that chunk of trees is one organism. They actually share an entire root structure, and the connections to that root structure are very complicated. And so that is an interesting network. This is one that actually I think is more important than it sounds, because for quaking aspen, learning about quaking aspen is interesting, but it turns out that something like 80% of plants participate in a mycorrhizal fungus symbiosis, where they create, with this fungus, they create an extended root network that connects the plants with themselves. And among this 80% of plants are most of our crops. So understanding these networks is also, I think, a big deal. Sort of as a riff on transport structures, ant colonies, and actually more broadly, the pathways that we build in three-dimensional buildings, also make, so for the architecture, it's much more ordered. But for something like an ant colony, and if you really want, you could buy this at art.com. This is an aluminum casting of the ant. This is another very complicated three-dimensional network. To sort of connect to material science and condensed matter physics a little bit, sand piles, granular matter, the way that you transport load from the top of something like a sand dune down to the base through a disordered media like sand, ends up creating a very complicated three-dimensional network. This is a picture taken from Bob Berringer's homepage, who does this nice research on photoelastic beads. So the beads, as a function of the stress and the direction of the stress in the beads, they emit light. And so you can actually see there's a giant bed of these beads, and then put some stress on the whole thing, and you can see that instead of just some nice gradient or some nice simple ordered transportation of the load through the system, you get a very complicated network structure. And so this is something I'm going to return to. And then finally, this is going to be, if you want a single thing to keep in mind, and I'm going to return to this as well. But if you want a single thing to keep in mind throughout most of the time, vasculature, mammalian human vasculature, is a big model system for these kind of networks. So the typical anatomical picture of vasculature is one in which it's a tree graph, right? Where, it's two tree graphs that are stapled together, right? You have your heart, and then your arteries start at your heart, and they branch, and they branch and they branch and they branch. And eventually you're at the capillary beds. And in the capillary beds, they connect to the very ends of the veins, right? The arteries connect to the veins, and then it's just the reverse all the way back, and that's it. That's the typical picture in a usual basic anatomy textbook. That leaves out some very important details, particularly in the organs. All of the organs, including the skin, except for the lungs, you get very complicated, loopy, reticulated network structures. And so this is a nice data set. This was the first data set of a mouse liver vasculature. This was taken by a grad student in the lab. It's done with serial sectioning and microtome, and you have to do the bulk face microscopy. It's a very, very, very complicated project. It was his PhD thesis. And so the reason why, obviously vasculature is an important thing. You can think about disease processes, things like that. And in particular, practicing doctors know qualitatively, kind of just by pattern recognition and experience, that they can identify the difference just looking at the vasculature between healthy liver, cirrhotic liver, and cancerous liver. So there's something there that's structural and that you can identify somehow. And that doesn't have a quantification. It's not something that we've been able to model. It's still a major open question about how you can approach that. So the first way one might imagine approaching a problem like this is just to take what that simple map onto a tree that exists in 2 dimensions and just push it up to 3D and just be done with it. So what does that mean? Well, hopefully the lighting you can tell, there's this one link here is white. It should be this one's special. And that one's special because we're imagining that that's the weakest one. That's the one we want to cut. And so if we just follow the prescription that I laid out from 2D, we would want to merge together the tiles that are incident on that link. And so which tiles are those? There's this one coming out of the screen towards you. There's one on the right. There's the one going into the screen away from you. And there's the one on the left. And so if you merge those tiles, that gives you a structure that is not a tile. It's not even a manifold with a boundary because it's doubly leaved, it has this weird intersection. And this is after just one cut, right? You can imagine that once you start iterating this process, it's just going to get worse. You can get things with, that have, that are either, have non-zero first homology group elements, right, that have loops or that have completely closed spheres. You can have very, very complicated topological objects that are not at all tiles anymore, even apart from any local problems with the foldings. You might protest that this was completely the wrong way to proceed, and you should have done that from the start, because what did we do in 2D? We had tiles, and we cut their edges to make tiles move together. So when you move to 3D, of course, that's not going to work. What you need to do is take cells and cut faces, cut tiles, and have the cells move together, right? And so you could do that if you can identify a cellular structure in the first place, which is not a given for a 3D network. But even aside from the questions of identifying a cellular structure, there's the issue that the actual physical data that we care about, the network itself, lives on the edges. And so if the network itself lives on the edges, and the tiles and the cells are, in some sense, an abstraction, there's no sense in which you can correctly identify which tiles to cut. What does it even mean? There's no, you can try to cook up something with some curl of the flow or whatever the weights are in the field, but it doesn't work. So you need something a little more sophisticated. So what we're going to do, and I'm going to give you a quick little refresher on a couple of elements of graph theory, just because I think it's worth it, and it's going to help explain the idea behind how we could validate this problem. So, excuse me. Can you sit a graph in space? So far we've talked about networks, 2D networks, 3D networks, and of course there's the class of networks that have gotten the most attention over the last 10 to 15 years, which is the totally abstract social network style, hyperlinked internet style networks. And so there's sort of a sort of starting point question, which is, can we take all networks, or can networks always live in 3D space? Is somehow the set of 3D networks complete? which you might not think it is. But a simple construction called this is a classical thing called the book representation, shows you that it actually is. So for a really big complicated network, what you can do is you can imagine aligning the nodes of the network along the spine of the book. For a really big network, you probably want to use a book like War and Peace, so it's big. And then for every edge, each edge in a network connects to 2 nodes. And so for every edge, you assign an individual page of the book, and it goes, the edge starts at one of the nodes on the spine, goes out into its own page, and then loops back around to the other node on the spine that it is connecting. And so you have a structure for any network at all that lives in 3D without the edges crossing or touching each other, which is what you need for a graph to be embedded. So that's fine. It's a complicated, basically useless construction. This is just an existence, right? This is saying, okay, you can do it. So now that's embedding in 3D. If you want to embed a graph in 2D, there's a special word for a graph that embeds in 2D, and that word is planar. So a graph representation is called planar if it embeds in 2D, that is, none of the edges cross in the plane. And so K4, this is the complete graph on 4 vertices. So it has, every vertex is connected to every other vertex, and there's 4 of them. And this representation of K4, this is the one you usually see, is not a planar representation. However, a graph, not a graph representation, but a graph is called planar if there exists a planar representation. So can you ever even write a graph as embedded in 2D? And for K4, the answer is yes. You can just move one of those 4 vertices in between the other 3 to make something that looks like a projection of a tetrahedron, and then there's no edge crossings and it's embedded. Okay, so this sort of begs the question, maybe you can just embed all graphs. Maybe the answer is to take your 3D graph, embed it into 2-space, and then do the procedure. Just do your cutting on 2-space. But that's no good. I chose K4 for a reason, because it's sort of the last complete graph that you can do. The complete graph on 5 vertices admits no planar representation. No matter what you do, no matter how you try to arrange things, you end up forcing a crossing somehow. And actually, Kuratowski's theorem guarantees that as the number of nodes in the graph gets high, the measure of the expected planar graph goes to 0. You get, basically get vanishingly unlikely to find a planar graph for large graphs, given some flat background, some flat prior. It's unclear how you define that. So of course, for these vascular networks, or for any of these other complicated 3D networks, for ones that you care about, that are large and extent, they have many nodes and many edges, there's basically no way it's going to be a planar graph. However, just to point out the final little bit of the background, this is a 2-part background. This part of the background. You can, if I took K5 and instead of just trying to do it in the plane, if I try to put it on a torus, so if I identify this side, this side, then you can do it, right? So you can just cut across the periodic convections, and you can write it in there for the process. And so this sort of is suggestive of what we're going to try to do. So ultimately, we want to try to find a way to take our graphs, our 3D graphs, and map them into a natural state, which I'm going to have to talk about in a second, but some kind of natural state where they're living on a surface, right? Where they're not just in 3D, so they're on a surface, so they're locally 2-dimensional, and locally tiling makes sense, and that you can then identify tiles and cut tiles and create a map. So I should add just a little bit of nomenclature. This doesn't sort of matter, but you might just out of pure curiosity, if you want to look it up later. The genus of the simplest surface on which one of these graphs can live is called the graph genus. Not particularly creative nomenclature, but it works. And the last little point, which is of course going to come up because it matters, is that the procedure of mapping a graph onto its a representative in the graph genus, so on the surface, and actually even just identifying what the graph genus is an NP-hard problem. So algorithmically, you have to do one of the typical tap dances around NP-hard problems. You sort of can usually be sure you're doing it, but aren't guaranteed. Otherwise, you do something crazy. And now I told you there's going to be one other brief refresher. The other brief refresher is on something called the cycle space. This bit is related to finding a natural taking a natural subunits of the graph and using them as the tiles on the surface of the graph genus. And so the cycle space, this is a general thing. We're going to build up a little bit to the natural objects. So this is just an example graph. Everything I'm about to say works for any graph, embedded or otherwise, but this is obviously just a 2D graph just to make it, you can see it much more cleanly, not unlike the mathematical undergraph. So what is the cycle space? The cycle space is a vector space over Z2. And so you should think about the elements as the sets of loops or combination of loops that live on the graph you're working on. And so this loop is an element, this loop is an element, or both loops at the same time is an element. And the reason why it's over Z2 is you actually, instead of loops, you represent it as assigning zeros or ones to all the edge of the graph in such a way that whenever there are ones, the ones have to be part of some closed loop. I'm telling you it's a vector space. Well, the vector addition is done by edgewise summation over that zeros and one representation. So here, if you had this element and this element, then when you do the summation, this edge gets a 1 and a 1, and we're over Z2. So the sum becomes this. And so this looks, and by design, this should look an awful lot like coalescing two tiles like we did in the very beginning of the whole story. You can generate, it's a vector space, so you might be interested in bases. And of course, bases are nice. So you can generate a basis from any spanning tree of your graph. Just to remind you, a spanning tree is a subgraph in which every vertex is visited once by the subgraph, and there are no loops. It's a tree. So this here is just an example spanning tree. There are, depending on if you count by vertices or edges, there are exponentially or super exponentially many spanning trees available. So there are lots of possible basis sets for this space. And so here's one. Here's a basis set that we're going to generate from this tree. The way you do it is you go through the tree, and for every edge that is not in a tree, you add it to the subgraph, and you find the loop that you made. And so if I add this edge to the tree, I made this loop. Okay, now I throw this edge out, and I go to the next edge that wasn't in the tree. I add it, I find the loop that was made, it's that one, etc. And so for the tree that I wrote here, this is the set of basis elements that you get. And again, this tree was actually chosen somewhat by design. If it weren't for this big long one, just to show that it's you don't always get a tiling. If it weren't for this big long one, this is really, really close to a tiling. And a tiling, of course, is a basis of a two-dimensional graph. If all the tiles are there, then you can build up any loop that you'd like out of the summation of the tiles. And so that is suggestive of what we want to say about the natural basis, the natural objects in the graph that we want to study here. And so in 2D, what we did was we looked at the tiling cycles, and we operated on them somehow. And so there's a privileged set of basis vectors, a privileged basis, in fact, that you can define by saying, I want to look at the basis that minimizes the total edge usage counted with multiplicity. That is to say that I want to look at the basis, so if this basis element is using 4 edges, and this one is also using 4 edges, and we'll count them all, right? We don't throw away the fact that we're reusing this one. So that's what I mean by with multiplicity. And so if you minimize your basis set over the edge uses with multiplicity, that's a uniquely determined natural object in this space, and it maps directly onto the thing that we cared about in 2D. Right? It recapitulates the tiling in 2D. And so now to give you a slightly more complicated example, and also to sort of describe, once we graduate from 2D to 3D, what is in this minimal basis? What does it mean? First, we can ask how many elements are there in the basis. And so that is going to be given by the total number of edges in the system minus the number of edges that were in the spanning tree, which is b minus 1. And then just to remind you, this is the formula for the Euler character. G is the genus, v is the number of vertices, e is the edges, f is the basis. And you can combine these, it's straightforward, it's algebra, to get this relationship. And so this gives you a separation of the basis vectors. You get a bunch of tiles, and you get something that is arising from the topology somehow. So what does this mean? Maybe it's something visual is more effective. So here, again, this is a graph on a torus. So we've identified the sides. You can do the face edge, you can do the graph counting, 36, 72, and 36 for the vertices, edges, and faces given here. A torus is genus 1. And the number of basis elements must be 37 by the figure above. And so it turns out that you get all the tiles. That makes sense. Notice that the f-1 means you throw one tile out. This is because if you include all the tiles and you're on a compact surface, which now we're talking about compact surfaces because we're on surfaces in 3D. If you include all the tiles, then the sum of all the tiles is the zero vector. So you're letting know overdetermined by one element. So you pick one to throw out because we're minimizing the total length used by the basis. You throw out the biggest one. But then notice there's these. These are also basis elements. And they're degenerate. It could have been, instead of this, it could have been that for this particular graph, just because it's high symmetry. So why are these here? These are here because you have a non-trivial topology. You have, effectively, you have generators in the fundamental group for the surface. And so what that means, just sort of in the picture, is that you can go across the periodic directions of the surface. You can go across the handle of the torus, or if it's a more complicated thing, you can go across some path that is, you cannot contract onto itself, but returns to its starting point. And for each one of those, you cannot build it out of just the tiles. If I tried to go across the periodic direction up and down with just the tiles, I would not get this path. I would get two paths that go next to each other. And so since the cycle space is every loop in the graph, I have to be able to represent odd numbers of crossings of the periodic boundaries with some combination of basis vectors. And the only way to do that is to include the generators in the fundamental group. So this is, and that's it. Right? We did the counting. We know how topology works. So we have tiles and we have these generators, these topologically derived cycles. Okay, and so now actually we have all the ingredients that we need to make a complete story here. So what do? So we have our graph. We choose a spanning tree on the graph. If we know, we know what the edge weights are. We know which ones we're going to cut. Maybe we can actually optimize things a little bit with some foreknowledge. We use that to generate a basis for the cycle space. We rotate that basis onto the fundamental minimal basis that we talked about before. This is a procedure that's done using something called Horton cycles that Horton worked out in the 80s. This sort of operation of looking at these minimal bases was of interest in the graph theory community in the late 80s and early 90s. This is a technical point I can talk about at the end if you're interested, but it's not really relevant. It's just a technical operation to do the rotation. Then you have to, in the end, we want to coalesce the tiles. So far we just have the list of basis vectors. And so we don't know which ones are tiles and which ones are the topologically derived cycles. And so we need to separate the tile basis vectors from the topological basis vectors. This is the point where the NP hard tap dancing comes in. It turns out that for a certain restricted set of graphs, you do this in such a way that you are, for large graphs, you know how controlled the odds are that you make the wrong choice are. And I'm going to talk about this in a couple slides. But basically the prescription is you take the edge you're cutting, you look at all the tiles that are coincident on that edge, and you choose the shortest two. Right? And the idea being that topological cycles that have to span, globally span some direction across the space are going to be long, and the tiles are going to be short tiles. And it turns out that for the right, again, for a subset of graphs, you can quantify exactly the error rate and control basically for for a large enough graph, you know that you're probably okay. And this is, you also know that this is the best you can do because this is an NP-hard problem. And then, so now you can coalesce tiles at this point. And then you map to a tree, and you can do whatever analytics on the tree you like. The whole thing runs, for those that care, in polynomial time. Otherwise, I wouldn't have to say anything about NP-hard. Okay, just to sort of reiterate, to echo the picture from before where we built up the tree, just to sort of repeat myself a little bit, but now in 3D. You do the edge ordering, you have some 3D graph or some, imagine this is some little sub-piece of a larger 3D graph. You do the ordering, So this, purple and light blue, it's really hard to see on this projector. And then you cut, and even though the shapes are kind of funny, the tiles are funny, right? It actually looks, in a way, it looks like you could have been one of the cases where I said, oh, this is good at the beginning when I showed the big cubic structure. But really, it's not also this tile and also this tile. It's just this one and just this one that have been identified by moving through that minimal fundamental cycle space basis. And then you iterate and build up a tree in the same way. Also to point out that the algorithm doesn't care about any affine transformations of space. Right? It's primarily topological. So long as you're not doing topological transformations, you're not messing up the connections, you can do any funny business with the space, any kind of funny filter on the images that you want. And also, perhaps more importantly, the algorithm is not sensitive to small perturbations in the magnitude of the weights. Right? The way the weights are used is as an order. Which edge do I cut? What's next? And so long as the perturbations to the magnitude of the edge weights don't pop any of the edge weights past each other in the order, then the algorithm's not going to see it. Okay, so the primary way I'm going to talk about the characteristic tree quantification for the rest of the talk, and it's sort of ongoing research to look into the efficacy of more quantifiers. But is this an object called the topological asymmetry. And so the idea here is that you go over all the nodes, and you assign each node, because this is, for all these trees, it's always going to be a binary tree, you assign each node this value, where Sj is the largest number of leaves. You have its two direct descendants, and each of those descendants ends up in some number of final spots. And so you take the largest one minus the smallest one over the largest one. And so the idea is that for a very symmetric graph, this quantity will be 0, right? Because you'll get, the largest one and the smallest one will be the same. And for a very asymmetric graph, this quantity will approach 1. So this is basically, and then you do a weighted average over the generations of the tree, so that you don't overly excuse me. You don't overly privilege the information from lower down vertices. But the basic idea you should keep in mind is close to 0 is a nice, just direct binary switching. Everything's totally symmetric. And close to 1 is something in this funny ordered sense. And that something like this looks like, if you remember, I pointed out a sort of hierarchical loop ordering in the leaf picture at the very beginning. That looks kind of like this, and this is different, where you have some sort of global ordering of the loops, or the order where the strength of the edges of the loops is. So instead of that little 1D case, for 2 and 3D versions, this is what some typical edge weight assignments are going to look like. Topological asymmetry is on the x-axis, that's what I just described. On the y-axis here is something called the average vein length. So this is not a quantifier of the tree at the end, this is just a quantifier of the placement of the edge weights just in the raw graph. What this tells you about is you put in a cutoff on the edge weights, and then you look at all the edges that are above that cutoff and look at the average number of consecutive edges above the cutoff, the average vein length. So of course, for high average vein length, you'll have the thick parts will all be connected in some long way, and the asymmetry goes in the same way as it did for the 1D case that I showed a second ago. And this is sort of, as I pointed out before, somewhat harder to understand just by looking at it, but you can see the same sort of features for the 3D cubic graph. Again, this is just to typify the coordinate space that we're going to look at. Okay, so we can run the algorithm. Here's a network that is sort of already living on a torus. You can pick a random spanning tree, you get elements like this, and then you rotate onto the minimum weight basis, and everything works beautifully. You find individual tiles, you find that the topological cycles shrink down into the smallest possible units that can be done. And now, finally, to circle back to what I said about the failure cases, and importantly, to talk about the restricted set of graphs that I'm going to talk about. you can prove that this works for. The restricted set of graphs are 3 regular graphs. So a 3 regular graph is a graph where every vertex has 3 edges that are associated with it. This, from the point of view of all possible graphs, this is a huge restriction, right? Only 3 regular graphs is a very, very small subset of all graphs. However, most of the physical graphs, basically all the biological graphs are 3 regular because of the way development proceeds. You just get binary branchings throughout the development of a vascular system. And anytime you get a reconnection, you just get a point-to-edge reconnection. So you get 3 regularity just for free for basically all the biological graphs. And for some of the other graphs, they're not 3 regular, but the degree distribution is tight and low. So you get a very low standard deviation for the degree distribution, and the average number is low. And so those properties together, I haven't proven it, but those properties together, I'm pretty sure are enough to give the same features. I think that the problem comes in when you get scale-free graphs, which are graphs that, for the most part, you don't care about if you have an embedding space. Right? So I think that it might not work for social, not for sound graphs, but for embedded graphs, mostly fine. You're definitely fine for 3 regulars. And so, just to reiterate, this is the Euler character formula again. For a 3 regular graph, the number of edges is intimately related to the number of vertices because, of course, there's 3 edges in a vertex, and then you don't want to double count 2. So you can move things together and get this relationship for the average number of sides in a tile on a 3 regular graph. And so long as the genus isn't high, for a large number of vertices, this collapses onto something 6 or just above 6. And so you can use just a regular hexagonal graph as a ground state to study all the possible graphs. And you can get to any graph of the same genus that you started with, any 3 regular graph of the same genus that you started with by applying these perturbative units. These are known, depending on what subfield you're in, these are known as either T1 topological rearrangements. This is what sort of soft matter jamming community calls them. Most of you might be more familiar with them as, this is a dislocation. This is a dislocation dipole, and it's also a disclination quadrupole. All the same thing, just one location. But you can iterate many of these perturbative units to create any 3 regular graph of the same genus that you started with. And so, how can it go wrong? Right? So now we have a way to kind of look at, systematically look at the possible space of graphs. How can that prescription that we gave before, where we're assuming that topological cycles are long compared to the cycles that make the tiles, what messes that up? So the 3 things that could mess that up are, you could just start the whole torus, or one whole topological direction could just be really small. Right? You could have a whole lot of these perturbative units could coalesce on one site, so all the disclinations could pile up, all the heptagonal disclinations could pile up over and over and over again to give you a really, really, really good tile. Or the dislocations could pile up over and over and over again to give you varicosity, where for the most part you have a thick handle, but suddenly for some little region of it, the handle gets really thin. And so you can work out the statistics for all these cases, and it turns out that for the thin handle case, you get that the probability of having a problem goes like 1 over the square root of the vertices. So it doesn't fall away super fast, but fast enough. And the other 2, I didn't write this down, but the other 2 fall away extremely fast, exponentially fast. And so the thin handle is by far the one that's the biggest problem. And for a 3 regular graph, it's not that bad. Okay, so now I'm going to show you. Okay, good enough. I'm going to show you some test data. So we made some surrogate networks with surrogate edge weight choices of 2 torus. Made one in just sort of a random space. These are both 3 regular configurations. So this is 3 space. Then randomly throw down points and then construct a 3 regular graph based on them and on a torus. And then we look at a bunch of edge weight assignments. So you generate the same list of edge weights, and then you assign them to the network either just completely at random, that's A here, in a linear fashion. So you take the biggest one, then you take the next biggest one in such a way that it's connected to the biggest one, and then so on and so forth with some percentage chance that you stop and start somewhere else. So that's B, this one. You can do the same thing, but don't allow yourself to ever cross yourself. You can cross linear bits that you're done with, that you randomly moved on to a new one, but you can't cross yourself. So that's B. These two, by I and by any past possible measure, are impossible to tell apart. And obviously I'm telling you that because we don't tell apart. And then there's something that I'm calling evolved, which you get by taking a random starting point and then doing just sort of a dynamical update rule on the graph. You think of it as some Higgins-Roussel network with some pressure amounts, and you can just update based on you solve the system as it currently stands over many. You go every possible pair of a source and a sink, and then you solve all the pressures and all the flow rates, and then you take those flow rates and you introduce an update to the conductances based on how much flow rate there is, and then some decay, so that you can get stuff that eventually pairs off that isn't being used. This actually is here's a separate work that we did. This is a reasonable model for the Physarum, the dynamic Physarum. Okay, so for those set of surrogate data, surrogate weights, and in the same coordinate space that I showed before, here's the random state. So high asymmetry and low average vein length. Here's after the evolution. The average vein length basically doesn't change, but the asymmetry basically vanishes. You get a highly symmetric final states out of that. And then here are the two that I said were very hard to tell apart. There's still a little bit of overlap region. And in fact, you must get this because some iterations of the self-avoiding ones are never going to self-avoid, right? You randomly won't ever encounter itself, and it actually will just be one of the same graphs. So you do have to get some sort of area where you're not sure, but you actually do get a relatively strong separation for a good chunk of it, which is cool. Oh, and I should say, gamma is these are just different strengths on the positive reinforcement for the adaptation. The higher, the stronger. And just to look at that a little bit more closely, on the previous graph, the final positions of the adaptive networks, they ended up in the same spot, but actually this kind of speed through the characteristic space is different. See the orange and the blue are the different strengths, and so the orange is the stronger one. It is, at some intermediate time, is almost completely separated from the blue on its way to the same final destination. And sort of as an inverse of, so for the linear and the self-avoiding linear, it was something that you couldn't tell apart with anything else, but we can tell apart. As sort of an interesting inverse comment on that, there's also something unifying. You can use this to unify things that you wouldn't have thought were unified. Here, this is the final state of the edge weights for the evolved adaptive networks. They're completely different. And yet, there's still something structural that's the same about them. There's something that unifies these graphs, that if you looked at with traditional means, you would have said that these are just totally different graphs. But there's something that is very, very similar, sort of deep structures. Okay, and now to finally, I'm going to cap this off with a couple examples of ongoing work with actual real data. So to return to Sandpile's case, you can look at excuse me. You can look at some of the things that's done in the jamming community. There's different states you take random disks. These are bi-dispersed disks in these cases, and this is a hexagonal network surrogate. You can make some force contact network out of the disks, put it under either just uniaxial stress or possibly isotropic pressure. This case, I think this is periodic boundary condition, so it's almost certainly isotropic pressure as well. And then look at what happens with the network structure. And so here, these are a bunch of actual jam configurations, this one. Here, these are a bunch of the networks that you get by looking at the states of self-stress of the system. And so, has anyone heard that term before? Or should I say something about it quickly? No? Wait, Sir Whitman? Yeah. Okay. So the states of self-stress of a system are the number of different stress configurations that can exist freely while the system is still static. So, for example, if you had a network like this, this network, well, let me just go to the final case. So if you had a network like this network, imagine these are all springs that are all at their resting states, right? You can put this, you can stay completely static if you put these guys under compression, and these guys under compression, and these guys under extension. Right? And so in any amount of that linear combination remains, keeps all the vertices and the edges exactly where they are, and it just builds up. It just builds up internal stress. And so you can do, there's a simple degree counting that's related to the number of constraints and the number of degrees of freedom, and you can work out the difference. You can't directly work out the number that you're going to get, but you can work out the difference between the states of self-stress and the zero energy modes, where it can just move without changing the length. And so it's become sort of fashionable in the jamming community to think of actual jam configurations as just sitting on the eigenstates, one of the eigenstates of self-stress. There's some privileged eigenstate of self-stress. That's what it does. That's what these jamming configurations are. That's not true. So these are the eigenstates of self-stress. This is the actual thing. They're different. And again, with traditional means, you can't put these apart. And this is just there's sort of a popular super simplified hexagonal mesh version that sort of can recapitulate some bulk elasticity properties, but not all of them for a system like this. And just to show that the structural parts of the network for this was very different, almost random, actually, if you remember where the random configuration sat from the previous graphs. And transport networks, yes. You can also look at, have this data on coach and rail networks in the UK. These are the weights here, are the speed of the link in the network. And you can look at, you can run the same procedure to compare them, and just to see if things are been organized differently, if somehow the economic pressures have led you to kind of arranging things differently in the way that you create the networks. And lo and behold, you do. The green, the large data points are the actual data sets. So the big red square, the big blue triangle, the big green triangle are the actual data sets. The other data points are randomly picking some subset of edges and swapping the weights. So this is sort of introducing a little randomness. You still keep most of the graph the same, but you add a little random noise to it. And the difference between the blue and red here, these are both trains, but the red, you throw out some of the hair, you have some of the very, very small stuff. You just start with a hair set. And basically, that doesn't change anything. But the real coach network and the real rail networks are extremely different. And I think it's an interesting observation. I don't have, one of the things I want to look at going forward is to understand, to sort of go through systematically and explore this space and understand exactly what structural or structural motif or subset type things you can learn about a graph or about a structure from the location or the difference in locations in the space. But just the fact that they're different. And now just to talk about a couple other systems. So some of the ones I brought up before, and also food webs. This is one of the ones that sort of sits somewhat far from the three regularities, so maybe is going to be questionable, but I think is worth investigating. And actual architecture, either as a design principle going forward, or just to understand how how topologically certain structures work better than others in a new way. And then finally, a quick advert. I've also done a lot of work on shape programmable materials, where you take something called liquid crystal solid, where you have liquid crystalline order in the material, but it's also a solid because it's a polymer mesh with cross-links. And if you're clever about arranging the director field, you can get all kinds of interesting, you have a flat sheet, you get all kinds of interesting crazy shapes, pyramids, and cones, and anticones, and spirals. I think there's a lot of cool opportunity for device design, and if you're interested in this, there's an article in Physics Today last month, January, that I wrote with one of my collaborators that covers this stuff at a sort of good, broad overview of it. And that's it. So thank you so much for your attention, and I'd be happy to take questions. Yeah.
I lost towards the end the like what was the original goal of so was it to create a specific property like coverage of veins or something, or characterization?
Characterization.
Characterization.
The goal was to find a way to quantify with the quantitative method, characterize these complicated things.
So what is the characterization going to lead towards?
So the idea then, and the hope, is that with this characterization, and I've begun work with, for example, a couple different labs at Rockefeller in neurovascular processes, where you have a really nice iDistro system data set of just regular healthy brains, and then another lab that looks at stroke brains. And so looking at where those network structures sit and are different, and if you can actually look at stroke brains that are either just post-stroke or just pre-stroke, and you find signifiers there. I mean, I think there's a lot of room for understanding both just network function, why is it that the network is complicated, and in what way exactly is it complicated, and also how network dysfunction causes other things, right? So obviously stroke is a big deal, but it's believed that there's a vascular component to autism. It's believed that there's a vascular component to most forms of dementia and Alzheimer's disease. Right? That's just in the brain. There's lots of other similar cases in other vascular systems.
So in other words, those are kind of tricky, delicate characteristics. They're not like a boom in my brain or something, right? So those are missing links in some bizarre way. Or...
Yeah, well, I mean, so one of the hopes, for example, in the stroke case, right? So certainly, in some cases, a stroke is just, one link ruptures and everything is bad.
Yeah.
But I think that you also, there's a strong chance that there's structural changes lead up to that event, right? That you can use it as a diagnostic, sort of, an early warning style system. Anyone else?
I'm reminded of some work on spin glasses 30, 40 years ago, where they, in order to understand the structure of spin glasses, they would embed it. This is David Nelson. Embedded in some higher dimensional space, 4D, where they would impose some kind of crystalline order. Does this connect?
That's a really, really interesting question. I've thought a little bit about the way that you can look at blue phases in liquid crystals as, again, it's sort of the same thing. You can embed it on S3, so you can go to a higher dimension and you have some funny boundary conditions. You have an exact solution for the map in space. You have some funny topology. It's sort of, the idea to do it this way was sort of inspired by that stuff that David Nelson did, and stuff that, the stuff on the blue phases, things like that. It's not obvious that there's a direct connection. I think it was really cool if it turned out that there were. It's something we're sort of looking for, but keeping an eye out for some kind of, but the answer is I don't know. I think that's a really cool idea, but it's certainly not obvious. If there were a direct connection, I wouldn't put that in here somewhere. It would be too cool not to mention.
Yeah, I was just interested. You were talking about the studying the vasculature in the brain, right? Something I'm even more interested in is studying the neural connection, the connections between the neurons and how, basically figuring out how we think.
Yes.
Right. And I mean, there has been a lot of work in
absolutely
artificial neural networks and stuff there. So could you apply your analysis because in the neuron transport, right? The signal transport is dynamic. Yes. It's not like the train waves over the vasculature, but you always have kind of you can split it up by how much flow goes through.
Right.
So kind of your weights would change of the connections. So I'm thinking, have you thought about applying this
I have.
Actual,
I have, yeah. So the spike trains, right? You can certainly look at spike triggered averages, right? For the spike trains, there's ways to extract meaningful weights from the spike train data, as far as the usage of the wings and things like that. And you would certainly want to include the dynamic component. You wouldn't want to just look at all-time static average for how the snake gets used. you want to look at it evolving in time, with the dynamics, and look at how the characteristic maybe moves around in time as some neural subcircuit does some computation.
Because I know people have looked a lot at, like certain regions in the brain getting activated, right?
Yes.
To kind of understand what people are thinking, and if you see a picture of a loved one, like a different region lights up. It would be interesting to see if your analysis picks up certain patterns when you.
It's something that's very interesting. It's something I have thought about. One hurdle is that depending on which neural subcircuit or which neural section that you're talking about, some of them are some of the cases that are very far from granular. We have a very wide distribution of the degrees of network. However, there are some other different neural regions that are much more complete. And I think that is very interesting. And actually, with the lab that I'm doing some of the nerve vascular data on, they actually have a data set of axonal projections that I'm also analyzing. So there's some sort of beginnings of that as well. It's a cool idea.
I have a simple question about the light of your graphs.
Yep.
Bring it back.
Yeah, I could try to find it. Sure. Do you remember which?
Very close to the end.
Okay. Is it one of the ones I really did? Was it this one?
No, the one you have a asymmetry number. No, you got this one. Well, something similar here.
Yeah.
Now you have another one also. You have a topological asymmetry. How do you define it?
Oh, the topological asymmetry was this. Yeah, I didn't actually. I for some reason I omitted the word topologically, but that's just this. So you go to each node, and because we're assuming a binary, you get a binary tree because you only merge two files at a time. You go to each node and you compare on each of the two branches from that node. It has some number of endpoints eventually, right? And so you take the difference of those two numbers. So here's 4 minus 1, here's 2 minus 2, and you divide by the larger of the two to normalize it, right? And so then that gives you. And then to do the whole thing, you then do a weighted average over where you take into account the number of generations bacular, so you can adjust for how much of an opportunity that you have. But if you only look at the last generation, you don't get anything. If you do the second last generation, you also don't get anything. So you can normalize out by, you don't want to overweight those. If you average over a node, you want the average. But this typifies the actual information where. So this is going to be 3/4, right? 4 minus 1 over 4, and this is going to be 0, right? And so for the ones that are 0, the ones that are highly symmetric will always be 0. And so as the higher the thing is, the more asymmetric it is. So yeah, that's what that. Yeah.
Is there any connection between the hardness of the algorithm and weights? So could you come up with a special weighting for, let's say, higher regular graphs that makes it an easier problem? Distributions of weights or something like that?
That's an interesting question. I haven't thought about that angle. My gut feeling is to say no. The hardness of the algorithm lies in the topological transformation, and the weights just tell you what order that critical thing. But if you could somehow ensure that the weights were less likely
There's some
to lie,
correlation in weights, right? Spatial correlation.
Exactly. That if you know what, I think what you can do, I don't think you can win overall, but you can you could arrange the probabilities in such a way that if you're right, you're more likely to be right later, and if you're wrong, you're more likely to be wrong later, right? So that each individual time the same odds occur, but you can correlate your errors, so that then if it goes wrong, it goes super wrong, you can tell, and if it goes right, it's even more likely to go right. So I think that you can, with this sort of spatial correlation of the weights, you might be able to arrange things. But then it's hard to imagine if you're actually analyzing a real graph, you can't play with the weights in that way. Right? The weights are given to you and you have to make do. But if you're doing something by design or trying to understand the sort of deeper significance of things, and you have that freedom to play with the weights, then yeah, that might be interesting to think about.
What does NP hard mean?
NP hard means non-deterministic polynomial time solutions.
So it's a bad thing.
It's a bad thing. It means that there's no. It doesn't mean necessarily that it's exponentially hard, in complexity, but effectively means that. And it usually means, so it means it's a subclass where you can usually check if a solution is right, given a trial or an explanation. You can check in polynomial time. That's what the non-characteristic is. But yeah, basically the way to think about it at a sort of simple level is that it's exponential. Things blow up in time.
Okay, let's bring our speaker again.